Ancient sailors told tales of massive tempests at sea. Even experienced mariners couldn't grasp the true scope of what they'd encountered. This comfortable notion of storms as regional disturbances persisted until the space age. Satellites revealed a truth that redefined atmospheric power. We don't live beneath ordinary weather systems at all. Earth regularly spawns rotating giants so enormous they can engulf multiple countries at once. Many hurricane systems stretch across hundreds of kilometers, and some grow far larger. These aren't just big clouds. They're organized atmospheric monsters with hard edges and steady structure. At peak size, some storms spread wide enough to cover huge swaths of coastline in a single sweep. From above, the spiral bands look carved into the sky. The center stays tight while the outer arms keep feeding in. These storms hold their spiral over vast ocean distances. They move slowly enough to track, yet fast enough to arrive before people feel ready. Each band pulls air inward like spokes on a wheel. When viewed from space, the spiral can look like a galaxy made of cloud. What happens when you measure a hurricane's heartbeat? The most shocking revelation emerges from inside these storms. Pilots describe the eerie calm of hurricane eyes. The instruments tell a colder story. At the center of every major hurricane lies something that defies everyday experience. The pressure drops so far that the air feels hollowed out. Normal sea level pressure feels steady and heavy. Inside the eye, that weight can seem to loosen. This isn't just a measurement curiosity. The collapse pulls air inward from all directions toward the center. It accelerates as it approaches, then bends into a spiral and locks into a fast ring around the calm. The storm feels like a moving cavity in the sky. Rising air carries moisture upward. High in the clouds, that hidden heat releases, and the upward lift strengthens. The center can deepen over days, and the pull tightens again. The hurricane becomes a mobile atmospheric vacuum cleaner. It holds sharp pressure gradients across huge distances. Night after night, it keeps generating the same circulation that feeds devastating winds. Close your eyes and imagine the fastest wind you've ever felt. Maybe a storm that knocked over garbage cans. Perhaps a night when trees leaned and creaked. Now push that force into a different category. Hurricane winds don't just blow. They race at speeds that make driving feel slow, and they keep going. The air becomes a continuous surge, not a brief burst. You can hear it in the constant roar and feel it in the pressure against skin. The storm becomes an atmospheric racetrack around the eye. The fastest winds gather in a tight ring, and the whole system can rebuild itself while it runs. A new eye wall can form around the old one. It contracts inward, and the spin concentrates into a smaller circle. The destruction potential turns unreal at the top end. At Category 5 strength, buildings can lose walls and roofs in moments. Loose objects become flying hazards, and the sound of debris can blend into the wind until it feels like one solid scream. Here's a meteorological riddle. What creates the same spiral winds, generates the same pressure collapse, and follows the same physics, yet goes by different names depending on which ocean it crosses? The same storm that Atlantic regions call a hurricane becomes a typhoon in the Pacific. Indian Ocean storms earn the designation cyclone. Same rotating fury, different names. Same destructive potential. Atlantic and Eastern Pacific storms use the word hurricane from Caribbean languages and histories. Western Pacific storms use typhoon, rooted in local terms for great wind. Indian Ocean systems use cyclone, drawn from an older word for circle. The naming changes, but the shape stays familiar. Meteorologists still classify strength in a consistent way, tied to sustained winds. The physics remains the same whether you're tracking Hurricane Katrina, Typhoon Haiyan, or Cyclone Tracy. Same heat engine, same rotation, same potential for catastrophic destruction. Earth runs an annual storm schedule with unnerving consistency. Every year, the oceans produce between 80 and 100 tropical cyclones. During peak season, it can feel like one rotating storm after another somewhere on the planet. The Atlantic hurricane season officially runs from June through November, but the Atlantic is only one part of the global pattern. The Western Pacific can stay active for long stretches, sometimes year-round. Other basins peak around local seasonal shifts in wind and rainfall. Despite these regional differences, the global total stays surprisingly steady. Some years the Atlantic quiets while the Pacific grows busy. Other years the pattern flips. Yet the yearly count tends to hover in the same range, as if Earth keeps a rough quota. Peak activity arrives in late summer and early fall, when ocean warmth runs deepest. Multiple storms can spin at the same time across different basins. On some satellite views, the globe looks dotted with spirals at once. Climate scientists watch these totals for patterns. El Niño years often shift activity away from the Atlantic and into the Pacific. La Niña conditions can tilt the balance the other way. Year after year, the storm factory keeps turning, guided by ocean heat and the moving flow of the atmosphere. Hurricanes are incredibly picky eaters. They won't touch cold water. They refuse lukewarm conditions. These atmospheric gourmets demand ocean temperatures of at least 26.5 degrees Celsius before they'll even consider forming. That's roughly the feel of a warm bath. Below that line, potential hurricanes fizzle out like wet matches. The ocean stops feeding them. Above that threshold, evaporation surges. Water lifts off the surface fast, carrying heat into the air. That stored warmth gets released again when the vapor turns into cloud. Scaled across a whole warm patch of ocean, the energy feels endless. The engine turns smoothly when the heat supply stays steady. When the water cools, the supply thins, and the spin loses its bite. But surface warmth alone can fool you. A storm wants heat that lasts, not a quick warm skin. It needs a deeper pocket of warmth beneath the chop. Ocean currents keep that warmth moving. They slide it across long distances like a hidden river. Some paths stay warm for days, and storms follow them. The Gulf Stream carries tropical warmth northward along the U.S. East Coast. The Kuroshio Current does the same work in the Pacific. These warm corridors become storm corridors, where the system can keep feeding while it travels across the basin. The equator presents hurricane formation's most frustrating paradox. Here lies the warmest ocean water on the planet, perfect fuel temperatures year-round, abundant evaporation, ideal atmospheric instability. Yet hurricanes refuse to form right on the equatorial line. They need Earth's rotation to teach them how to spin. Near the equator, that lesson feels too faint to hold a clean spiral. Welcome to the Coriolis effect, Earth's invisible nudge. Moving air bends right in the northern hemisphere and left in the southern hemisphere. That bend helps a storm wrap itself into a ring. Picture a spinning merry-go-round. You throw a ball straight, but it seems to curve from where you sit. Air does the same kind of curve on a rotating world. So tropical disturbances can look fierce and loud. They can dump rain and light up with thunder. But without that steady bend, they struggle to lock into hurricane form. Northern Hemisphere hurricanes rotate counterclockwise when viewed from above. Southern Hemisphere cyclones spin clockwise with the same stubborn consistency. The spiral direction holds like a rule written into the sky. Hurricanes are architectural perfectionists. They want calm construction conditions to build tall spiral towers. Strong winds aloft act like bulldozers, knocking the structure sideways while it's still trying to rise. This construction problem is called wind shear. It's the mismatch between winds near the surface and winds higher up. When that mismatch stays small, the storm can stack its core into a clean column. When it grows strong, the storm gets pulled apart. The top slides off the base, and the center never firms up. Most would-be hurricanes die right here. Sometimes the jet stream drifts over the tropics and makes the air hostile. A storm can have warm water beneath it and still get its head torn off. It leaves behind the ragged remains of a system that never got to organize. Surface warmth alone won't build a hurricane. These atmospheric monsters need a deep reservoir of heat below the waves. The ocean mixed layer has to stay warm enough, not just at the skin, but down into the body of the sea. That depth feels like the difference between a match and a fire that keeps eating. The mixed layer acts like a thermal battery, holding sunshine stored over time. It gives the storm something to drink from even after the surface gets churned. As winds strengthen, the ocean gets whipped and stirred. Heat gets pulled up from below, and the storm feeds harder. But that stirring can also drag cooler water upward and dull the fuel line. Fast-moving storms can outrun the cooling. Slow movers can sit over one patch and drain it. From above, the surface may look perfect, while the deeper heat is already too thin to keep a major storm alive. The atmosphere runs its own highway system for storm development. Many roads lead to a shifting belt called the Intertropical Convergence Zone. It wraps around Earth, sliding north and south with the seasons. In the Atlantic, many hurricanes begin as tropical waves rolling off West Africa along this belt. Trade winds from both hemispheres meet and press humid air upward. The air keeps rising, and the sky keeps building. It feels like a giant mixing bowl that never stops turning. Disturbances pass through, and most fade. A small fraction tighten into something organized if the rest of the conditions stay gentle. When the zone stays steady, it sends out a steady stream of seed storms. When it gets disrupted by other patterns, the factory floor goes quiet. The ocean can stay warm, but the launches stop. This is why hurricane seasons feel so patterned. There are windows when the belt sits in the right place over the warmest water. Outside those windows, hurricane development becomes rare. Step inside nature's most bizarre architectural achievement. The eye is a circular pocket of calm, floating inside a violent spin. It feels wrong the moment you imagine it. Nearby winds can tear apart buildings and uproot trees. Yet the eye can stay so tranquil that birds slip through it. Some eyes feel calm enough for a plane to drop into. Hurricane eyes typically span 20 to 60 kilometers in diameter. But size doesn't guarantee peace. A tight eye can sharpen the surrounding winds. A wide eye can make the shift into chaos feel slower, almost sneaky. Air keeps spiraling inward and tightening its turn, but it never fully reaches the exact center. The spin holds it off, and the fastest winds lock into a ring around the calm. Inside that ring, the pressure sinks. Warm air climbs through the middle like a chimney. The sideways rush gets pulled upward, and the center can go oddly quiet. Pilots on Hurricane Hunter flights describe the moment as walking into a cathedral. Cloud walls rise high around a patch of blue, and the silence feels unreal. But the structure can wobble, shrink, expand, or vanish without warning. Eyes can fade during replacement cycles, and the calm can arrive like a trap. People step outside thinking it's over. Then the backside of the eye wall arrives with winds from the opposite direction. catching them in the open at the worst possible time. Welcome to the hurricane's engine room, a circular wall of thunderstorms where the storm does its harshest work. The eye wall is where the most serious damage gets made. This ring rises just outside the eye and marks the zone of maximum wind. Everything else is background compared to this tight core of fury. Eye wall storms don't behave like ordinary thunderstorms. They stack upward like atmospheric skyscrapers, building a wall you can't see through. Inside that wall, heat keeps converting into wind over and over without a pause. The roar never really stops. The eye wall runs on a microclimate that feels detached from normal weather. Temperatures can drop hard as air climbs. Pressure can shift fast enough to make instruments glitch. Lightning can keep firing, yet stay hidden behind dense cloud. Thunder keeps folding into itself in that circle, and the rain turns vicious. The strongest winds don't always hit at ground level. They can ride a little higher, slamming into upper floors and tearing at roofs and treetops. The eye wall also behaves like the storm's control ring. When it contracts, the whole system can tighten and intensify. When it expands, winds can ease even as the storm spreads outward. Some hurricanes grow a second ring around the first. Then the storm reshuffles its core, and intensity can swing in ways that feel sudden from the ground. Hurricanes are cosmic artists working with clouds instead of paint. From space, the bands curl like a spiral galaxy, clean and deliberate, its beauty with teeth. These aren't random cloud smears. Spiral bands extend outward from the core in long, curved arms. They keep their shape even while the whole storm rotates. Each band works like a moving belt of heat and moisture. It gathers energy from far out and feeds it inward. The bands slide around the center, staying curved, staying organized. The spiral keeps a steady angle as it opens outward. You can watch it on satellite loops and feel the order inside the motion. The pattern looks calm even when the ocean below is boiling. But the arms serve a brutal purpose. Each band acts like a tributary, collecting warmth and moisture and channeling it toward the eye wall. The core keeps getting fed, again and again. The spiral shape also builds a lopsided storm. On the right side, rotation stacks with the storm's motion, and winds tend to hit harder. On the left, it subtracts, and the bite can soften. That imbalance is why one coastline can get shredded while another area nearby feels strangely spared. Ever watched a figure skater pull their arms in and spin faster? Hurricanes play the same trick, just with air instead of muscle. The center tightens and the spin jumps. As air gets drawn inward, it has less room to circle. The turn speeds up anyway. The storm concentrates that rotation into the eye wall until the wind sounds like a machine that won't shut off. That acceleration isn't optional. The inward pull keeps tightening the curve, and speed builds with it. Compact storms can feel especially violent because the rotation gets squeezed into a smaller space. But contraction has limits. When the core shrinks too far, the balance breaks down. The storm starts tripping over its own spin. Some hurricanes peak right before that threshold. Then the inner structure collapses, the eye changes, and the winds can sag fast as the core reorganizes. What goes up must come out. Hurricanes manage their own exhaust high above the chaos near the surface. Without it, the storm can't keep breathing. Air rises through the core carrying heat and vapor. Near the top of the atmosphere's lower layers, it can't keep climbing. So it spreads outward, sliding away from the center. Up there, winds can curl outward in the opposite direction of the surface swirl. It feels like two stacked systems working against each other, smooth and relentless. When that outflow is clean and strong, the storm stays efficient. The upward pull feels easier, the center pressure can deepen, and the winds can harden. When the outflow gets blocked or messy, the storm can stall even over warm water. Satellite images sometimes show the outflow as thin, wispy clouds fanning outward from the center. They stretch far beyond the visible core, hinting at how wide the storm's influence can reach. Hurricanes pull off an invisible heist. They don't rob banks. They steal warmth straight from the ocean through a process most people never notice. When seawater evaporates, it carries hidden thermal energy. That hidden payload is called latent heat. Hurricanes gather that stolen energy and turn it into wind. The stealing happens nonstop across a huge patch of ocean. Evaporation keeps lifting warmth off the surface, molecule by molecule. Latent heat stays hidden until the vapor turns back into liquid. Then the stored energy comes back out inside the clouds, right where the storm wants it. You can't see latent heat. You can't feel it directly, but you can watch the storm deepen as the ocean keeps feeding it. As winds pick up, evaporation surges. More vapor rises. More energy gets carried upward. The storm builds strength on its own supply. Every time vapor becomes cloud, heat gets released. Hurricanes ride that release over and over inside their tallest towers. When rising air cools enough, droplets form. The latent heat that was taken from the sea comes back out. The air around the droplets warms, and the updraft stiffens. The towers act like vertical conversion factories. Air enters low, loaded with invisible vapor. Higher up, that vapor turns into cloud, and the energy reappears. The rising column leaves lower pressure near the surface. That tug draws in more warm, moist air from the ocean. The flow keeps circling, feeding the next tower. Condensation also changes volume. Vapor takes up space. Droplets don't. Not the same way. That shift adds a quiet suction that helps keep air moving through the storm. Hurricanes are heat engines. They convert warmth into motion, the same basic idea behind power plants and turbines. Warm ocean water acts as the hot reservoir. The upper atmosphere acts as the cold sink. Air cycles between them, and the storm extracts work from the gap. A hurricane's core cycle is simple. Water leaves the ocean as vapor. It rises, it cools, it condenses. The released heat keeps the rising motion alive. The engine runs best when the ocean is warm and the air aloft is cold. When sea surface temperatures climb past 26.5 degrees Celsius, the storm has room to pull harder. What makes it eerie is the self-tuning. When the ocean offers more fuel, the storm can widen its intake. When the upper air cooperates, the cycle tightens. Above warm tropical water, the atmosphere can feel like a loaded spring. The surface air is hot and wet. The air above is cooler and drier. Meteorologists call that stored lift kept-up, convective available potential energy. In the storm zone, it feels like air that wants to break loose and run upward. Give it a trigger, and the surface air surges. It rises, cools, and starts condensing. Each new droplet releases heat, and the climb accelerates again. That's how the towers get so tall. The updrafts can become fierce enough to shove cloud tops into the highest layers of weather. Without enough convective energy, storms stay flat. With it, the sky stacks into deep columns that can build spiral bands and the walls near the core. A mature hurricane runs on energy scales that feel unreal. The flow of heat and moisture through the system can rival vast fleets of human power generation. Most of that budget comes from latent heat. Evaporation loads the air. Condensation releases it again, The cycle repeats hour after hour across the storm's reach. The winds add another piece. Circulation turns that released heat into motion, and friction grinds some of it back into warmth near the surface. The storm weakens fast when the fuel line breaks. Over land, the moisture supply collapses. Over cooler water, the engine loses its bite. And even then, hurricanes are only tapping part of what the tropical ocean holds. The reservoir underneath them is enormous. The storm draws from it and keeps moving. Hurricanes follow a strict grading system that measures their potential for atmospheric mayhem. The Saffir-Simpson hurricane wind scale reads like a report card for storm violence. It rates hurricanes from Category 1 troublemakers to Category 5 civilization erasers. But unlike school grades where C means average, Category 3 hurricanes can already demolish entire neighborhoods. This grading system doesn't mess around with participation trophies. Category 1 storms snap branches and peel roof shingles. They feel survivable with solid preparation. Category 2 storms rip up large trees and turn loose objects into flying debris. The damage spreads fast, and it feels less negotiable. Category 3 storms cross into truly dangerous territory. Well-built homes take major structural damage, and mobile homes become traps. Storm surge can push seawater inland and swallow coastal streets. Category 4 storms bring catastrophic winds that strip trees and shred buildings. Most homes become uninhabitable, and power can stay out for months. Category 5 storms don't just damage buildings. They erase them from existence. Coastlines can be redrawn, and recovery becomes a full rebuild. Not all hurricanes read from the same playbook. Some storms choose concentrated fury, packing devastating winds into compact areas. Others spread heavy weather across enormous regions. These are different kinds of disasters, and they feel different on the ground. Compact hurricanes keep their strongest winds in a tight core. Hurricane Charley showed that style, carving a narrow corridor of catastrophic damage. Large hurricanes stretch wide and keep pushing weather outward. Hurricane Ike showed that reach, bringing dangerous conditions far from the center. They move like slow, rolling disasters that take a long time to pass. The size difference changes how evacuations work. Compact storms demand precise planning near the hardest-hit zone. Large storms force whole regions to move, even when the center stays distant. Hurricane size also changes how land interferes with the storm. Compact storms can cross narrow peninsulas and keep their core over water. Large storms brush coastlines with their outer bands, weakening earlier but lingering longer. Sometimes hurricanes undergo a shift so dramatic it feels unreal. Rapid intensification is the meteorological version of Dr. Jekyll becoming Mr. Hyde. A storm that felt manageable suddenly becomes a major threat within a day. These metamorphoses are among the most dangerous surprises in hurricane forecasting. They can catch coastal residents off guard. The official definition requires wind speed increases of at least 55 kilometers per hour within 24 hours. Some storms surge even harder, with a single day that rewrites the forecast. The physics behind it come down to rare timing. Warm water, low wind shear, clean upper level outflow, and unstable air can line up at once. When they do, the storm tightens and accelerates like something finally unchained. Rapid intensification often happens over ocean hot spots, like the loop current in the Gulf of Mexico. These pockets feed the storm longer and deeper. The strengthening can keep feeding on itself until the storm hits its ceiling. Forecasting stays difficult because the threshold is chaotic. Small changes can flip a storm from steady growth to explosive strengthening. Sometimes there is less than a day between watch this and run. Occasionally, hurricanes reach a level of geometric perfection that feels almost staged. Annular hurricanes develop circular eye walls that form symmetric donut shapes visible from space. They look like a cosmic bullseye floating over the ocean. These storms form when the atmosphere stays unusually steady through the storm's depth. The eye wall turns round and clean around a sharply defined eye. Spiral bands fade or become so even they barely register. The setup is rare. Wind shear stays low, ocean temperatures stay uniform, and upper-level outflow stays steady. The storm doesn't get pulled into lopsided shapes, and it holds together. Annular hurricanes can keep that symmetry for days while staying remarkably stable in intensity. Hurricane Isabel showed that look in the early 2000s, holding its structure for more than a day. Their balance wastes less energy, so they resist sudden weakening. Only about 7% of hurricanes show true annular characteristics. When they appear, they look like weather built with a compass. Forget the wind. The most lethal part of a hurricane doesn't blow, it flows. Storm surge turns the storm into an ocean that moves inland. This isn't gentle flooding. It comes in fast, heavy sheets that shove seawater across streets and fields. Dry ground turns into churning water in a short window. Over open water. Hurricane winds don't just skim the surface. They push and stack it toward shore. At the same time, the storm's low-pressure center lifts the sea slightly upward. Together, it forms a traveling mound of higher water that rides with the hurricane. Hurricane Katrina showed what that looks like in 2005. Seawater rose into a towering wall along the Mississippi coast, then pushed inland with brutal force. It carried cars, boats, and whole houses like loose debris in a flood channel. The danger grows fast with storm strength and with shallow coastlines. A weaker storm can still drown low-lying neighborhoods. A stronger one can pour over buildings and crack concrete with raw, moving weight. Storm surge also arrives early. It can creep up while the winds still feel manageable, then jump in the final hours before landfall. People who wait too long can find their routes cut off while the worst wind is still on the way. Hurricanes act like an atmospheric fire hose. They can dump enormous rain over a wide region, fast enough to overwhelm drainage in minutes. It can feel like a city is being filled from above. Streets vanish first, then yards, parking lots, and lower floors follow. The storm keeps making that rain as it moves. Warm ocean water feeds constant evaporation. That moisture gets lifted into tall cloud towers, where it condenses and falls in waves. When the storm slows down, the same areas get hit again and again. Hurricane Harvey proved that in 2017, when it stalled over Houston, rain kept arriving in repeating bands hour after hour, until entire neighborhoods became shallow lakes. The heaviest bursts often sit near the inner core, but outer bands can still trigger flash floods far from the center. Mountains can make it worse. Moist air runs into a slope and gets forced upward, squeezing out even more water. Valleys can turn into torrents that erase roads and tear through towns. Inside the spiral bands, smaller rotations can snap into life. These are tornadoes that form quickly and scatter across the storm's reach. They often catch people off guard. Someone can think the main storm has passed, then hear a new roar rising out of a rain band. Hurricane tornadoes grow out of sharp wind shifts inside the outer bands. Different wind speeds slide past each other and create rolling motion. A thunderstorm updraft can tip that roll upright, turning it into a vertical spin. Certain parts of a hurricane produce them more often. The right front side is a common hotspot, where forward motion and rotation combine into stronger shear. Hurricane Ivan spawned 127 confirmed tornadoes across multiple states in 2004. Many were short-lived, but they appeared in quick succession, striking places that never hit the full hurricane core. They don't always behave like plains tornadoes. They can form faster, fade faster, and shift direction with little warning. That unpredictability makes planning harder when crews are already stretched thin. Hurricanes also send waves far beyond the storm itself. Long-distance swells can travel across the ocean and hit coastlines that never saw the hurricane. Surfers chase them. Coastal crews watch them closely. Inside the storm, sustained winds build huge waves near the core. Those waves then spread outward in organized sets, rolling through deep water with little energy loss. They can arrive days after the storm has moved on. A distant shore can look calm, then suddenly get pounded by powerful surf. Harbors can surge. Rip currents can intensify. The danger feels out of nowhere because the sky above you is clear. These swells show how far hurricane energy can travel. A storm doesn't have to be nearby to make the coastline dangerous. Hurricanes can also pull moisture into long corridors that stretch far from the center. These narrow bands act like sky rivers, carrying wet air into regions far inland. The transport runs through the spiral bands. They gather moisture from a huge ocean area and guide it down a more focused path. On satellite images, the corridor can look like a bright ribbon. It bends and snakes away from the hurricane, still feeding clouds long after the core weakens. That moisture can keep causing problems after landfall. Remnants can drift inland and keep dumping rain, especially when they link up with other wet air already in place. When those moisture corridors meet mountains, the rain can jump again. Air gets forced up the slope, cloud layers thicken, and water comes down hard on one side of a range. These sky rivers widen the hurricane's footprint. Even when the storm itself is fading, the moisture can keep reshaping weather far from the track. Hurricanes moonlight as Earth's most efficient heat delivery service. They run a thermal redistribution loop that keeps temperatures from snapping to extremes. Without this, the tropics bake while higher latitudes harden into ice. These storms help steady the planet's temperature balance across wide regions. Heat leaves warm tropical water and rides inside the storm's circulation. The transfer happens fast enough to matter on a global map. The storm loads up on warmth over tropical seas, then carries it poleward. That energy rides along the track and doesn't stay put. It spills out through condensation, warming air far from where the heat began. Across the Atlantic, many storms push tropical warmth northward along the U.S. East Coast. Across the Pacific, typhoons carry equatorial warmth toward Japan, Korea, and Eastern Asia. The effect shows up season after season across entire ocean basins. When storm activity drops in certain years, the pattern can feel different. Regions that usually get these heat deliveries can turn unusually cool when tracks shift. Areas that take more passes than usual can hold warmer air for longer stretches. Think of hurricanes as massive atmospheric traffic controllers. They don't only stir local chaos. They can bend wind routes far beyond the storm's own swirl. Their influence reaches outward and keeps traveling after the center fades. Momentum moves with the storm as it crosses an ocean basin. It carries spin from the tropics toward higher latitudes. That shift can tug on larger wind systems already in place. Jet streams, trade winds, and monsoon flows can all feel the disturbance. Sometimes the reshaping lingers well after the storm is gone. A strong storm that pushes far north can warp jet stream patterns. Weather systems can stall, or take unfamiliar turns long after landfall. The aftershocks can show up across Europe, North America, and parts of Asia weeks later. The storm also scrapes against the ocean surface, pulling at Earth's rotation in tiny ways. That rotational energy gets smeared into broad circulation changes, then fades out as heat. Even small timing shifts, detectable only with precision measurements, point to how much momentum these storms move. Active seasons often line up particular large-scale flow patterns. Quiet seasons tend to line up with different ones. The storms are not just passengers in the atmosphere. They leave fingerprints on the routes that follow. Hurricanes serve as Earth's most powerful oceanic blenders. They churn up deep nutrients that would otherwise stay locked in darkness. Without that stirring, wide tropical waters can go biologically thin. The mixing comes from wind-driven turbulence that digs far deeper than normal waves. Hurricane-force winds roughen the surface into a thick, foaming skin. Warm water gets pushed down and cooler, nutrient-rich water rises to meet it. That vertical swap drags phosphates, nitrates, and other nutrients into the sunlit layer. In the wake, chlorophyll can surge and stain the surface in satellite images. The bloom can hang on for weeks after the storm has passed. Those tiny plant swarms feed the entire chain above them. Zooplankton gather, then fish follow, and larger animals trail behind. The wake can look like a temporary feast laid across empty water. A single major storm can surface an ocean's stored nutrients on a scale that dwarfs most natural pulses. After Hurricane Katrina, phytoplankton blooms spread across the Gulf of Mexico and stayed visible from space for weeks. The ecosystem ate what the storm dragged up. The benefits can stretch beyond the immediate bloom. Mixing can connect organisms across depth layers and across distance. It can open brief windows for movement, survival, and adaptation. Earth runs with a subtle planetary brake system most people never notice. Hurricanes can slow the planet's rotation by tiny, measurable amounts. They steal a sliver of spin and spread it through the atmosphere. The transfer starts with friction between wind, sea surface, and the lower atmosphere. As winds sweep across vast ocean areas, drag pushes back against Earth's rotation. The extracted energy flows into changing circulation, then dissipates as heat. At peak intensity, major storms can shift Earth's rotation by microseconds. Atomic clocks can catch the change, even when no one can feel it. The number is small, but the moving momentum is not. Mass also gets rearranged around the rotational axis as air shifts poleward. The balance changes in subtle ways that affect rotational stability. It's like a skater changing posture, except the motion is made of air and water. Over longer periods, global storm activity tracks with small variations that astronomers monitor. Active seasons tend to pull more rotational energy into the atmosphere. Quiet seasons leave the planet's spin a little steadier. These interactions show how a single storm can touch a planetary scale system. The weather is not separate from the mechanics. It presses on the physics of the whole spinning Earth. Climate change gives hurricanes an engine upgrade without asking anyone's permission. As temperatures climb, ocean water warms like a boiler turned up year after year. Hurricanes feed on that warm water, so the fuel supply is getting richer. This could push future storms beyond anything most coastlines have faced. The warming itself can sound small when you say it out loud, but hurricane formation sits near a hard line. Small shifts can flip the outcome fast. Hurricanes need sea surface temperatures around 26.5 degrees Celsius to form. As that warm water line spreads, more places can meet it. The season can stretch too. Storm-friendly water can linger where it used to fade. Later this century, some tropical regions could run noticeably hotter. That kind of heat can support the strongest end of the Saffir-Simpson scale. It can also keep storms stable for longer. The ocean stops being a brief spark and starts acting like a steady furnace. We might need to invent new hurricane categories for storms powered by superheated oceans. The extra fuel doesn't just raise peak strength. It can hold that strength over long crossings, and it can keep the core tight when it would normally loosen. The drop-off in intensity could slow. Coasts might face long hours of top-end winds instead of a quick fade. And the most unnerving part is the pace. The warming can feel like it's picking up. Arctic ice loss and shifting ocean currents can stack into feedback loops. The fuel reservoir keeps warming, and the reach of that warmth keeps spreading into zones that used to be marginal. The map of safe water keeps getting redrawn. The atmosphere is becoming a more efficient water storage and delivery system. It's quietly upgrading hurricane rainfall capacity. As temperatures rise, air can hold more moisture. It carries a heavier load before it spills. Warmer air acts like a bigger water tank. That extra capacity turns hurricanes into stronger precipitation engines. They can dump more water faster, and the ground has less time to breathe. Hurricane Harvey offered a brutal preview when it stalled over Houston. It stayed in place and kept unloading rain. Neighborhoods disappeared under sheet after sheet of water. The feeling was not a storm passing by, but a storm camping out. The setup is simple to picture. Warmer oceans feed stronger storms. At the same time, steering winds can weaken or tangle. Some storms slow down or stall right on top of a city. Projections keep leaning toward heavier hurricane rainfall in a warmer world. That shift would crush drainage systems built for older patterns. Flood channels, pumps, and levees can get outpaced. The water arrives like an appointment you can't reschedule. The added moisture also changes the storm from the inside. More condensation releases more heat. Updrafts can punch harder, and the eyewall can tighten. Those feedbacks can push rainfall beyond what a simple more moisture story would suggest. Climate change is setting up a two-part hit for coastal communities. Sea level rises in the background. Storm surge rides on top of that higher starting line. The surge doesn't just arrive. It arrives already elevated. Future storm surges will begin from higher baseline water. That changes how far inland the ocean can reach. Even small increases at the start can spread the flood footprint wide. Flat coastlines feel this the most. The surge can travel farther across gentle slopes. Areas that once flooded at the edge can flood deep into neighborhoods. Critical infrastructure gets caught in that reach. Roads that once stayed usable can turn into channels. Modeling keeps pointing to a brutal multiplier effect. Storm surges that used to hit thousands can threaten far more people. Airports, hospitals, and evacuation routes lose their thin safety margins. What felt like a buffer starts to vanish. That's the real trap. Rising seas erase the room coastlines relied on. Storm surge physics stay the same, but the baseline keeps climbing. Global warming is turning the jet stream into an atmospheric drunk driver. It swerves and meanders. That chaotic steering can send hurricanes toward unexpected targets. Communities that rarely worried about storms can get pulled into the story. The jet stream normally acts as a guiding current. When that current weakens, tracks get stranger. Storms that would curve away can turn back. Forecasts can feel like they're chasing a moving rail. Hurricane Sandy showed how shocking that can look. It took a hard, unusual turn toward a major city. The steering pattern behind it held in place. That kind of stubborn atmospheric setup can trap storms in odd routes. The background shift is visible in the air itself. Polar regions warm fast, and the old temperature contrasts soften. The flow can slow down and start to wander, and those wandering patterns can persist. That opens the door to higher latitude threats. Parts of New England and eastern Canada can see stronger storms. Even some European coasts may face unfamiliar risks. Places outside the usual hurricane map may not stay outside. Climate change is pushing hurricane territory into new water. Storm formation zones can creep into places once considered off-limits. As ocean surfaces warm, the boundary shifts. New coastlines get pulled into the risk. The expansion is quiet at first. A patch of water that used to be almost warm enough becomes warm enough. Storms find fewer dead zones. They can hold together where they used to unravel. Observations already hint at storms peaking farther from the equator. That's a slow migration, but it matters. Preparedness infrastructure doesn't move as easily as water temperatures do. A region can be caught learning hurricane rules in real time. Models suggest this creep can continue through the century. Some European coastal waters may grow more supportive of tropical systems. The Mediterranean is already flirting with tropical-like behavior at times. That's a new kind of worry for places built around different storms. And it's not only where storms form. It's where they survive. They can carry dangerous strength farther north than they used to. Those impacts would feel unfamiliar. They would also feel personal. A storm doesn't care about a region's history. It only cares about the water and the air it's moving through.